This is review for the final. Day 5. All right, so in this section of Algebra 2, we made a chart. So I want to recreate that really quickly. And we're not going to do the entire chart that we made in our notes from this section. We're just going to kind of jot most of one down to save some time and space. But this is something that we have made before, in case you still have access to it. But there are questions that you will need this for on the exam, so in case you misplaced it, or maybe you missed that day in class, whatever the case may be. So I'll give you a minute to create that and then we'll fill it in. All right, so in this chart, these numbers are the exponent. These numbers are the bases. These numbers are the bases. So what it says is 2 to the second power, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. I won't write that in the rest of them, but I'm just kind of letting you know how it works. So that would be 4, 8, 16, 32, 64. So the next column will be 3 squared is 9. 3 to the third is 27. 3 to the fourth is 256. 3 to the fifth is 243. And 3 to the sixth is 729. Four squared is 16. 4 to the third is 64. 4 to the fourth is 256. 4 to the fifth is 1024. I don't believe the numbers are going to go much more higher than that, but you could certainly fill in more of this chart if you needed it. Five squared is 25. 5 to the third is 125. 5 to the fourth is 625. And 5 to the fifth is 3,125. That's interesting. They all have 25, 25, 25, 25. All right, and then 6 squared, 36. 6 to the third, 216. 6 to the fourth, 1,296. And I didn't calculate this earlier, but I'll do it now. 6 to the fifth is 7,776. So I chose to recreate this chart in case you didn't have it, because problems like this require that you have some knowledge about common bases and their exponents. We always want to rewrite the bigger base as a smaller base. So I see 32 can be rewritten as 2 to the 5th. So I'm going to replace that 32 with 2 to the 5th. I haven't changed the problem. I haven't introduced anything new. I am simply rewriting 32 as a base of 2.
And you put it in there.
All right, once I get these bases the same, I can set the exponents equal to each other and solve. Now, there's a couple of different ways you can solve this, but I always recommend subtracting the smaller amount of x's away from the larger amount as your first step. It's just going to make more sense for your brain to finish the problem, because you guys are used to having the x's on one side and then dealing with the numbers. That's kind of like what you focused on in Algebra 1. All right, so we're going to do that again. I'm going to show you another one. And on this next one, we're going to have to change both of the bases. So I'm checking out 16 and 32, and they have to be in the same column. So like, I see 16 is 4 squared, but that doesn't help me because 4 to some power doesn't make 32. So I have to find 16 and 32, and they are both a base of 2. So I'm going to have to change 16 to be 2 to the 4th, and I'm going to have to change 32 to be 2 to the 5th. So I rewrite both of them. 16, we said, is 2 to the 4th. And 32 is 2 to the 5th. Once those bases are the same, I can just set the exponents equal, and we'll be ready to solve the equation. I'm going to subtract 10x from 12x. So I get 2x minus 12 equals negative 20. Okay, so after the exponential equations, we learned about logarithms. And we learned how to rewrite a log as exponential. And we use this little whoop. You can even make that sound effect if you need to. Whoop. It might help you. I hope you're trying it at home. You're all on mute, so I don't know. I'm just going to assume. There's a bunch of woo whoop going on. Say it loud, say it proud. Y'all are so fun. Okay, so here's what it looks like. So we would say this out loud as log base 2 of x equals y. And to me, the most important part of that statement is log base 2. Because it reminds you where we're going to start. The base of our exponential is going to be 2. The exponent will be y, and the answer will be x. I'm going to give you a moment to write that down. All right, so when I rewrite, I'm going to make that loop. 2 to the y equals x. 2 to the y power equals x. There's my base. There's my exponent. There's my answer. So that's why that loop is important. Oh, I didn't make my sound effect. Okay, so we're going to use this idea to solve logarithmic equations. So first, I'm going to rewrite this as exponential. 8 to the second power equals x. Ooh. 8 to the second power equals x. And then to properly answer the question, you want to evaluate if you need to. So 8 squared is 8 times 8, which tells me the answer is 64. So on these equations, they sometimes put x in a different place. So like on this next one, log base 5 of 125 equals x. We're going to do the same process, but when we get to the answer, we're going to have a little bit of a different question. So first we rewrite 5 to the x equals 125. So this time, they're asking us about the exponent. 5 to what power?
You get to work?
No, I had to order an adapter. Equals 125. That's the question that it's asking us. So, actually, we just made a cute little chart. 5 to what power equals 125? Well, there's 125, so it must be 5 to the third power. So the answer would be 3, because 5 to the third power equals 125. Okay, so I've got one more for you. Log base x of 64 equals 6. So I rewrite x to the 6th equals 64. So again, they're asking us a slightly different question. What base to the 6th power equals 64? Well, I'll check the chart. So for an exponent of 6, it looks like 2. 2 to the 6th power is 64. So x equals 2, because 2 to the 6th equals 64.